Busting out of triangles, take 2. I screwed up the first one. I'm going to try to do a better job this time. Okay. So busting out of triangles. In your last video, we talked about triangle trig. And that's baby trig. And now we're moving on to grown-up trig, which is trigonometry outside of a right triangle. That means that we're going to be dealing with trig ratios of angles greater than 90. And so what does that even look like? Or what does that even mean, and why? Well, we know that there are angles that are bigger than 90 degrees. We know that there are angles which are bigger than 180 degrees, 360 degrees. What does that mean? Well, one thing it might mean is if you're sailing and you're having a nautical experience and you're going to turn your boat around, we would use degrees to describe that turn. And in this case, this boat is traveling this direction, and then it goes to traveling that direction. So that boat has traveled more than 90 degrees. That has made a 180-degree turn. So we need to be able to talk about angles that are bigger than 90 degrees. Similarly with a clock, if we talked about the second hand rotates more than 360 degrees. You know, every minute it goes 360 degrees, so every hour it does that 60 times, and then every day it does that 60 times 24 times. So clearly there are angles which are greater than 90 degrees, and we need to be able to deal with those in the same way that we deal with angles that are trapped inside a right triangle. So just like with finding slope at a point, mathematicians knew that they needed to work around to find ratios outside of a right triangle. Okay, so just to review again, the sine of an angle in a right triangle is equal to the height of the triangle, or the opposite leg of the triangle, over the hypotenuse. In this case, we're going to call our hypotenuse r for the radius of a circle, just like the second hand of a clock, that can rotate all the way through the coordinate plane multiple times. Okay, so we're going to call that the radius. This side over that side is equal to, this side squared over that side squared is equal to the radius. Okay, so we're just going to call that r. So clearly the sine of theta in this case is going to be y over r. Okay. Now, if I want this triangle to remain the same, but I want to be able to define this angle in terms of the second quadrant and the third quadrant and the fourth quadrant. So what can I do? I can flip this triangle over the y-axis and have the same exact triangle, same exact radius, but it falls in a different quadrant. Now, before we go there, I need to define an angle in standard position. An angle in standard position has what's called an initial side, and this initial side has two things. It's got its axis, its vertex at the origin of my coordinate plane, and it has its initial side as the positive x-axis. Always, always, always. Okay? And the terminal side is this side over here. This is called the terminal side. The ending side. Okay? So that's the terminal side. So we're going to rotate in the counterclockwise direction, and that is a positive angle. If we were going to go backwards, that would be a negative angle. So angles in the coordinate plane are actually like vectors. Direction matters. So positive angles begin on the positive x-axis with their vertex at the origin. And the terminal side is caused by going this direction for a positive angle, going that direction for a negative angle. All right? So what if our terminal side landed in the second quadrant, or the third quadrant, or the fourth quadrant? Okay, now we'd have angles that are bigger than 90 degrees. And what we're going to do here is we're going to take this triangle that we originally had, and we're going to flip it over the x-axis. So that allows us now to discuss that angle there. Initial side, terminal side, but now our trig ratio falls in the second quadrant. So now we're talking about this side over r. R is still the same. These sides are still the same, with one exception really, and that is that our x-coordinate is negative, but our y-coordinate is positive, right? Negative x, positive y. The value of x and y have not changed, just that the sign of our x has changed. So now let's talk about this angle here. Let's say we wanted to talk about that angle. Well, now our x is negative and our y is negative. Okay, and this coordinate here is negative x, negative y. Triangle is still the same. The side values have not changed. The radius has not changed. Think about it. The radius is always positive because it's a distance. It's a distance from the origin to this point here. Okay, if we squared negative x, squared negative y, we would get the square root, which is positive r. Okay, the distance is positive. Finally, if we wanted to talk about that angle there, this angle, woo, all the way around. In the fourth quadrant, notice x is positive again, y is negative, and our radius is still positive because the radius is always positive. So what you can see here is that the triangle doesn't change. The ratios remain the same, but the sign of the ratio will change. The sign of the ratio will change because our opposite side goes from positive to negative, and our adjacent side goes from positive to negative. Okay. So let's say that we were going to take the sine or cosine or tangent of theta in the first quadrant. We would get the opposite side over the hypotenuse, which is positive over positive, right? Y over r. Let's say we were going to find the sine of an angle in the second quadrant. We would get opposite side, which is positive y over r. Okay, so sine is still positive here. The sine of theta is still positive here. When we move to our third quadrant, we get the sine of our angle is negative y over r. So it looks like the sine of an angle that falls in the third quadrant is going to be negative, believe it or not. The sine of an angle that falls in the fourth quadrant is going to be negative y over r again. So the sine of an angle that falls in the fourth quadrant is going to be negative. But it's going to be the same as the triangle that falls in the first quadrant. It's going to be the same as the ratio for the triangle that falls in the first quadrant. Now cosine follows the same pattern as does tangent, except that since cosine is x over r, wherever x is negative, cosine is going to be negative also. Okay? R is always positive. And for tangent, tangent is y over x. So when one of them is positive and one of them is negative, that's when tangent's going to be negative. So you can think about that for a little bit. Here's a little mnemonic to remember when each of the trig functions, sine, cosine, and tangent, are positive. In the first quadrant, all trig functions are positive. In the second quadrant, sine and its reciprocal are positive. Sine's reciprocal is Cosecant, good. In the third quadrant, tangent and its reciprocal are positive. Tangent's reciprocal is cotangent. Excellent. And in the fourth quadrant, cosine's going to be positive, and cosine's reciprocal will be positive, and cosine's reciprocal is secant. Excellent. Good. You're learning very quickly. All right. So we're covering a lot of ground here in 10 minutes, and you have to remember that when I taught this in class, we spent a long time on it. So this is going to take a while, but you might have to watch this a few times to get it. We always talk about angles in standard position here. Okay? When an angle is in a triangle, the ratios are all positive. Okay? In order to sort of figure out how to get that obtuse angle that equals that acute angle, we use something called reference angles. So what does a 60-degree angle look like in another quadrant? Well, here's my 60-degree angle, okay? And I've rotated my triangle over that way. So if that's 60 degrees, what's that angle there? That's right, it's 120 degrees. So 120 degrees, the reference angle of 120-degree angles is a 60-degree angle, okay? There's my angle. All right, well, what about that angle there? If this is 60 degrees, what's that whole angle there? It's going to be 180 plus 60, which is 240 degrees. So a 240-degree angle has a reference angle of 60 degrees, okay? But it's in the third quadrant. Lastly, let's talk about this angle here, all the way around. That's 60 degrees, so what's that whole angle there? Well, 360 minus 60 is 300 degrees, okay? Has a reference angle of 60 degrees. Okay, so that means that a 120-degree angle and a 240-degree angle and a 300-degree angle are all like 60-degree angles. They have the same ratio as a 60-degree angle, sine, cosine, and tangent. But the sign of their ratio is going to be different depending on whether it's sine, cosine, or tangent, and whether sine, cosine, or tangent is positive or negative in the quadrant that it falls in. So that's going to take a little bit to digest, but so the sine of a 120-degree angle is going to be positive because sine is positive here. The sine of a 240-degree angle is going to be negative because sine is negative in the third quadrant. And the sine of a 300-degree angle is going to be negative in the fourth quadrant because sine is only positive in this quadrant and that quadrant. You need to think about that for a little while. Okay. So here's a definition of a reference angle here. Oh, we got Christmas colors. Okay. It is an acute angle. Always, always, always an acute angle, which is formed by the terminal side of a non-acute angle and the x-axis. So that is also very important. Reference angle is always between the x-axis and the terminal side. Okay? And a reference angle is always acute, because basically what we're doing is we're saying, okay, if we put this 120-degree angle back in the first quadrant, back into a right triangle, what would it be? What is it equivalent to? So let's do some practice finding reference angles. I always draw them first. So 140-degree angle. That's going to fall in the second quadrant. Okay? So that's 140 degrees. This is the angle we're talking about because we want to draw it between the x-axis and the terminal side. And so this is 40 degrees away from the x-axis. So 40 degrees is our answer. Okay? I'm going to have you pause the video I want you to try to figure out the other ones. You can't, there is no rule of like, oh, we always subtract from 180, or we always add to 180, or we always subtract from 360. Yes, you do all three, depending on the quadrant it falls in. So I recommend sketching the angle and then figuring out the acute angle between terminal side and x-axis. Okay, don't be foolish, not the y-axis. All right, kids, so I hope you got these all right. Notice, direction doesn't matter when we're talking about reference angles. Always positive. Reference angles are always positive. Okay? Reference angles are always positive. Direction doesn't matter because we're just figuring out if they fell in another quadrant, what would they be if we put them back in the first quadrant? If we put that right triangle back into the first quadrant, what would that angle be? Okay? So keep that in mind. Radians make finding reference angles even easier, especially with the ones that we're supposed to commit to memory. Okay, the thirds, the fourths, and the sixths are, we're talking about 30 degrees, 45 degrees, and 60 degrees. Those are the angles that we really care about. And so in radians, this is just insanely easy. If we have a fourth, the reference angle is pi over 4. If we have a third, the reference angle is pi over 3. If we have a sixth, the reference angle is pi over 6. Now, I hope that you're remembering that this is a 45-degree angle because they're quarters of 180. This is a 60-degree angle because they're thirds of 180. And this is a 30-degree angle because they're sixths of 180. So I'll let you figure out the rest, pause the video, and do the rest. I am going to bet that you got these right, okay? You should be starting to think, after the first video and lots of practice with radians, you should be starting to think in radians rather than in degrees. So here is the Quizlet that you can practice on. You can practice finding finding reference angles, and you need to get really good at this because the next phase is going to be, what is the sine of 2 pi over 3? And that is where your classmates have been confusing you when they're like, oh, I know what that is. That's a 60-degree angle, and so the sine of a 60-degree angle is root 3 over 2. And you all have been like, what? Wait, what? And we have to get you out of that place. Okay, so let's go practice, get really good, and stay tuned for the next video.